Okay, so welcome to a milestone in AMC's history. Yeah, so the class began, I started teaching in 2006, and the first evidence of that is right here. Yeah, so welcome to Saurabh Mhatre. Yeah,
Thank you.
right. So one of my earliest students. Yeah, and he got into NMIMS-BSSA, right? After he cracked the entrance exams, and BSSA had just started, Balonchit School of Architecture, NMIMS, and he went through that and then got into Harvard GSD, completed architecture from NMIMS BSSA, then Harvard GSD for product design, and then he has been in the US doing a lot of research, and he has a patent on his design also, the folding, the swivel folding, how would you call it? You can
deployable mechanism. I'll show some.
Yeah, sure. Coffee table, and like absolutely, like all the stuff that I wanted to do, I aspired for as a student. Like he's been cracking all that exactly the way I had envisaged. Yeah, so we got this opportunity that he's here, and I invited him for this presentation, and this will be a whole series of presentations from now onwards. Okay, the next one would be Yash. Yeah, so we have this series planned throughout life, right? So this is where I have been talking about AMC being different from your typical coaching classes. This is where it all starts. Aditya, you would be next. Yeah. Okay. And then Aditya, you would be next. Okay. And of course, Akshay is the hands-on real life project creator. So definitely we'll be, of course, be going to his sites also. Right. So all this is happening. Right. And Khyati would be coming up with her recently completed completion in the process of done. Okay, then you have to present your thesis, your pending. ठीक है, वो आ जाएगा, तब तक आ जाएगा once they present. So then full blast of the Indian aesthetics course and all that. Right. So all these things have been planned for all you guys. I'm really envious. I wish I was a student. This will be like literally we have now around 800 plus, almost 1000 students. Yeah. Since last 16 years, 17 years now of AMC. Right. So even if we were to have one such guest invited lecture once in a week, it will be 52 such sessions, right? With almost 20 times the number of guests that we can invite, right? So for next 20 years, अब से और कोई भी lectures नहीं होंगे तो भी next 20 years we are occupied, right? So with one guest lecture every week like this. Okay, so we are starting with the first in this series. So Saurabh,
thank you so much.
The stage is all yours.
Yeah, first of all, thank you for the invite, Sanjay Sir. I really appreciate all the support that you've given me from day one, since I was sitting there in SP classes for sort of, I always say that has been my beginning of my journey into design, and till this day, till this moment, I guess. Well, thank you so much. And again, I want to emphasize on the sort of the concept of community, how design, research, all of this, like how valuable community is. And I appreciate to see Sanjay Sir sort of developing that sort of community here for all of you guys. So, yeah.
Right. So he mentioned ST classes. So that is where I started teaching the first time over. It was a PCM class in Borli, and Joshi sir, like I'm really grateful to him for having me conduct a pilot batch over there for their students. So Saurabh was part of that batch, right? It was not here at AMC back then, right? And then after that first pilot batch, he said that we are no longer continuing with our with architecture. Our regular engineering and medicine itself is keeps us occupied. All our classrooms occupied, etc. And there are very few who opt for architecture in any case. So any enquiries that might come to us, we will forward it to you in case you are starting on your own. I was happy, and that way a lot of goodwill from Joshi sir of SP class. I am really grateful to him and thank him from the bottom of my heart that he has been sending students in the initial phase, so many students. So that's how AMC kept growing. In fact, the first few classes, hats off to the parents, that after my first introductory presentation, which I held at SP classes, they actually sent their bachas to this so-called non-class because I did not have any classroom space. Yeah, but they trusted me purely based on the presentation. And then the first few classes, because I was still searching for a space. Yeah, so the first few classes were outdoor sketching. क्लासरूम स्पेस ही नहीं तो कहाँ वो मालाड के कोई शॉपिंग मॉल के स्टेप्स पर एक आउटडोर स्केचिंग हुआ. देन द नेक्स्ट क्लास वाज एट भवंस कॉलेज टेम्पल, वो मंदिर जो है फ्रॉम भवंस, या एंड लाइकवाइज सौरभ इज आल्सो फ्रॉम भवंस. सो अंधेरी वेस्ट ऑफ भवंस. So उधर एक outdoor sketching हुआ. That way gradually then I got hold of a space. So it was at SPIT, the Sardar Patel Institute of Technology in the Bhavans campus. That's where I started the classroom space on a rental basis. Right. So that was the first batch. That first purely me with my students batch, and then I shifted. I realized that why pay this rent to this place. I could use the same money to modify my own space, which was at Four Bungalows. Yeah, my own residence. But in between that, before that renovation happened, it was being held at one batch happened at Yari Road. There was this that building was set up. By the way, there's a connection with Manoj from your domain. So there was this building in Popco. Yeah, Police Officers Progressive Cooperative Housing Society, Popco. That building was built by the actor Guru Dutt, his brother, for housing the crew of the movie called Pyasa. It was a famous movie. So all the crew was pulled up in that building, and in the entrance foyer there is a bust of Guru Dutt, the actor. Yeah. So that was where my art studio was, and I also started conducting the training from there for a short while. That was a rented space. I had taken it on rent, and that was also where my first art exhibition happened. All those paintings that happened at Jahangir Art Gallery in 2010, those paintings got created over there in that space. It was a 1 BHK again. So then later on, I shifted it my place at Four Bungalows, again a 1 BHK, where in at one point of time, I remember during the introductory presentation, people kept on coming. I had removed one wall so that it was a decently big space. Like you can consider half of this space. So that much to be converted into one single space with a lot of innovations. The swiveling table, that itself became a case study. One of the students from Kamlaraja had taken that as a case study for multi-use spaces. Right? So a lot of sliding stuff like this at home and various innovations like a bed coming down from there, etc. So it's a compact for living as well as for the class. And one day I observed one of the Sundays, it was absolutely jam packed, and some parents could not even attend, they could not even enter. Itna packed ho gaya. That was when I realized that I am doing something significant. Yeah. Anyways, so they had to return the next Sunday for attending the intro. It was that bad. Anyways, and 10 years back, we shifted here, right? 2013. So that again marks a kind of a milestone. And here we are. Yes, go ahead. So,
Okay, as Sanjay Mhatre mentioned, just as an introduction, currently I work as a research scientist at Northeastern University, but majority of the work that I'm going to show you is going to be the 10 years that I spent at the Harvard Graduate School of Design. And I'm going to highlight a few things within my journey which might be very significant to showcase who I am and what I do. So I guess ever since like school, I've always been very much sort of trying to keep shifting between the mindset of the creative versus the engineer. So in a lot of work that you are going to see, it's going to be an interesting blend of both. And majority of the works which I'm going to show you are trying to dig into the novelty of how having knowledge from multiple fields enrich your sort of like way of thinking and the projects that eventually you do. So within my sort of journey, some pivotal points were, I think I was in 11th and 12th trying to sort of go in the direction of becoming an engineer. I even went to the extent of like giving my CET, MHCET exam for engineering at that point, and I got good marks, but I decided that I don't want to do engineering, but I want to go into a more creative field. That was also to a certain level influenced by my dad and my sister being an architect, and I could associate sort of when they used to work, I used to like sit with them and make models. So that's why I decided to make the shift. So 2004, my sort of shift from engineering to architecture, as Sanjay Sir mentioned, that it was because of him that I got to know about BSSA. I was looking for architecture schools, and having done classes with Sanjay Sir, he mentioned that like, oh, I've been contacted by the school called BSSA, and they have asked me to teach graphics there. So why don't you check it out? So I was like, okay, well, and that's how I ended up sort of being the first batch of BSSA. Um, One interesting sort of thing about BSSA is that like because we were the first batch, we always call ourselves like the lab rats, where a lot of experiments were done on us, like how to go about design and things. But which for us was interesting because we got an amazing set of faculty who were teaching us, and majority of them had a lot of exposure from schools abroad. So they sort of tried to put a little bit of their learning into teaching us. Right after doing my bachelor's, I think throughout the course of my bachelor's, I got very interested into this idea of parametric design. How do you use computers to help and assist you in designing? And at that point, I knew that if I wanted to develop my interest further in that, I will have to go and do a master's abroad. And that's how I ended up going into the Harvard School of Design. And I got into this particular program called MDes Technology, which was all about learning all of the emerging technologies and see what role they play in informing your process of design. So that was one of my sort of biggest highlight of being in that ecosystem. Exposed me to a lot of interesting people, not just from design and architecture, but all across the board, from material science to engineering, roboticists, even people in the psychology department, etc. So that's like the best part about being in a larger ecosystem of a university, where it's very easy for you to come across people from different fields, then always stick to, okay, we are going to hang out only with designers, right? So that was one of the sort of biggest aspect. As a part of my 2-year master's, I ended up working a lot based on the courses I took with people from the material science department, and because of which I ended up doing my thesis on a topic very much embedded within material science. Based on that, I got a chance to, right after graduation, work as a research associate in the research lab at Harvard. And that's where majority of the work that I'm going to show you is going to be done there. And very recently, 2 months ago, I also changed my jobs, as my sort of next step is working in Northeastern University as a research scientist. So right now, in the future, the work that I'm going to be doing will very much be located in between design, chemistry, and biology. So sort of there's like a new field of biodesign, where how can you grow materials. So it's interesting, where I don't know if you must have seen people using mycelium, mushroom bricks, and these sort of, that's just like one of the example, but that's what I'm going towards. So to start off, what I already mentioned about the importance of transdisciplinary design, how there's a novelty to be working as a designer with people from different fields towards higher goals. Maybe one of the goals could be sustainability. So how can you as a designer and architect work with material scientists to, for example, develop a material which can be sustainable? So that's where I sort of place transdisciplinary design into. And again, all the work that I'm going to show you is not going to be something which is done by only me, but a lot of these projects somehow are a group and collective effort from the other people and colleagues in the lab. And I think it's very important to acknowledge that like a lot of these projects have a big sort of team supporting them. And that's why it's a work of all of us. So you're going to see this symbol very sort of prominent in a lot of my slides. This symbol, which you see in red, is typically used in chemistry to denote a dynamic equilibrium, where it shows that there's a constant exchange between the two entities on the left and right. And that's how I sort of place myself, is to be in a sort of equilibrium between multiple entities. One could be design and one could be science, constantly sort of dwelling between curiosity-based research, opportunity-based research, and applied research. Again, these terms might be new to you, but I will sort of give you by example what these terms mean. And also constantly shifting between ideas of top-down design and bottoms-up design. So I'm going to be explaining to you 3 projects. One dealing with 3D printing of ceramics that my former lab has a lot of expertise in, and which I call more of what do you call, like a bottoms up approach. And then another sort of category of 2 projects, which is designed for minimal assembly. So 3D printing of ceramics. So why 3D printing of ceramics? Right now, 3D printing is one of those technologies which has sort of percolated each and every domain that you see. Majority of the machines that you see 3D printing, 3D print polymers, which are plastics. In order to convert polymers and convert them into an object layer by layer, a lot of plastic is heated and reshaped. So when you look at how can this technologies be scaled, can this technology be applied to buildings, it doesn't make sense to use like tons and tons or kilograms of heat them up. A lot of energy is gone. So what kind of materials can 3D printing be used for? So what kind of materials can be used in 3D printing? Bigger things, larger things, architecture, for example. You must have seen a lot of these videos where people are 3D printing concrete and making buildings out of concrete, which is great as one step. But concrete also as a material has a lot of carbon emissions. So as a lab, we try to look into, can we look at ceramic as a material, one of the oldest material known to man, and can we use that material to be 3D printed for architecture? So as I mentioned earlier, our lab has a lot of history working with different aspects of ceramics, and in the interest of time, I'm going to just go through 2 projects, which is ceramic morphologies and Janus printing. So in ceramic morphologies, we ended up using 3D printing of ceramic. So imagine instead of like the smaller table machines you see, imagine like a larger syringe where you insert clay, and by inputting certain codes, how can you make the machine print that 3D object? Right now the video is not playing. I'm very sorry for that, but you can see, oh, it is playing. Okay. So how, when you look at these emerging technologies like 3D printing, ceramic industry has always been associated with the idea of mass production, where you produce the same object in large quantities. And these emerging technologies, what they give is that they look at mass customization. How can you use the same amount of material, but instead of producing the same kind of object, how can you produce unique different objects using the same volume of material? So this is like the pavilion which we made. I'm not going to go too deep into this, but sort of get deeper to the next phase where we made a pavilion. And during that process of 3D printing, we also came across the point of what kind of opportunity can it give us. So I'm going to showcase that opportunity based on this project called Janus. So it's very common for us as researchers to look at other fields to get inspiration from them. So one of the interesting fields to look at is the field of food production. A lot of the sort of companies and like infrastructure has gone way past in terms of making all of these snacks which you have in your sort of daily life, where a lot of these food products are produced through processes of extrusion. And using different shapes of nozzles, etc. So we decided to look at how can we first see how this idea of dual extrusion has been used in food versus even other industries. So a lot of the cable wires that you see are also produced in a similar fashion. And then we decided to see, can we try and look at the same process using ceramic? So we try to see, okay, let us see what novelty we can get by having the ability to print two different bodies of ceramic together inside one single nozzle. And as you can see the setup here, that we have a 6-axis robotic arm, which is something which is very commonly used in automobile industries to put cars together. But in the research lab, we use that as a tool. How can we print big with these sort of technologies? And as you can see, the nozzle is specifically interesting because you have both the bodies coming together into one single stream. And ceramic is also an interesting material because we call it a living material, because even when you print ceramic, it doesn't stay in that shape. Based on the moisture content, etc., it also shrinks with time. So we started to look deeply into how the design of the nozzle could sort of give us different affordances of how the bead could be. So as you can see that you have like the left and right coming, you can get a bead like this. Based on the direction of printing, it can facilitate different sort of structures on the beads. We also had another idea of what if we had two nozzles where one was inside the other, can we get a bead like that? But that's something that I would not be talking about. But on the left side, where we have the two nozzles printed side by side, this is how the clay behaves when you push it out. And we do a lot of physical prototyping in order to get more control over the parameters. So some particular parameters in this process could be, what is the diameter of the nozzle out of which the clay comes out? What is the speed of the robot that it's printing? What is the extrusion rate? How fast is the syringe being pushed? Right? These are parameters which we try to get more control of to be able to know exactly what is going to be printed. So you can see sort of certain examples of how the two beads being printed next to each other, how interesting that could be. And again, as you can see there, that a lot of these parameters are interdependent. So for example, if I have a nozzle size of 8 millimeter, if I'm making like a small bead of 8 millimeter, if I'm printing at a certain speed, if I increase the speed quite a bit, the width of my bead is going to decrease. So there's a direct relationship between what the width of the bead is to the speed. So how can you control different aspects like porosity, etc., based on that? So experimenting in the 2D plane versus experimenting in the 3D plane to come up with interesting sort of objects. And also sort of showing how what we design in the computer, right? Like the sort of fidelity of the control that we have now, where we design that we want to print an object in digital space like that, to rendering to try to see what will it be in the digital space, to be able to get that sort of control to have it match with the actual physical object. So yeah, just based on what I earlier mentioned, that having the ability for rotating the fourth axis, the nozzle, what sort of differences it makes to what you see from the top versus the side, and going to end up making like this proof of concept to show how much control we have. Like, can we use the rotation of the fourth axis to be able to print a well-defined shape? So this is a quick video of that same. Yeah, if you have any questions or something that you don't understand, just raise your hand. It's okay to disturb me in the middle. Yes. These two different materials are similar. So they are different bodies of clay. Their compatibility is very similar to each other, because they need to be of a certain similarity so that they don't shrink very drastically as compared to each other. So they need to shrink very similarly, or you will get a lot of cracks if one body shrinks very drastically differently to the other. So as you can see, sort of like the proof of concept, and that's like the sort of final tile. So my next sort of phase of projects is uh, this deployable mechanism called Kiriform. Before I dive into the project, I want to tell you about two concepts about the difference between rigid mechanisms and compliant mechanisms. Rigid mechanisms, one of which is what you see a lot of gears. They contain a lot of parts. They are not easy to assemble. They also do take a lot of maintenance for when parts wear out. But as compared to that, compliant mechanisms are easy to manufacture, are more durable, and can be easily sort of deployed. So some of the examples of compliant mechanisms is, as you must have seen in your house, like the shampoo bottles, etc., which are made of one single material, but they perform a lot of different functions. So Kiriform is a patented system that uses material elasticity to and geometry to go from a flat form to a deployed 3D form. So it relies on the concept of buckling. What buckling is, how so bending is when you have the force from the top of the beam, for example, that you must have seen. But in case of buckling, the force is actually on the cross section of the beam, and that's how it differentiates itself from bending. So the best part about this mechanism is that it can be cut out of flat sheets, and both the different cutout sheets can be used to portray that sort of behavior. And as you can see, this is a live example of the same. And maybe after the talk, if anyone wants to have a closer look, please let me know. But so it can be deployed very easily, and it can be actuated, which I showed you, one from the perimeter or one from the central pivot. And we also have a sort of good parametric model. So that's what we always keep doing, right? Like shifting dynamically between the digital workspace and the physical workspace. Because we know that everything cannot be done on the computer, especially when you're dealing with materials. So you have to follow a sort of constant process of do something digitally, make a physical model, try to see if it works the way you want. And there should be like a dynamic shift between the digital and the physical. And for the sort of application, so again, like what I earlier mentioned about the certain projects which we are always trying to find the solution to a problem, but then there's a different category of research where we explore and try to find opportunity. So this mechanism, which is what we found was like, oh, super interesting. And now we developed it to the point, now we are trying to find, okay, what can this be used to solve, right? So these are different sort of applications that we looked at, ranging from small sort of medical devices, how can you cut this into like some tiny sheets inside the body, maybe some speculative applications of can this be used as a deployable zoom lens for your phone cameras, maybe optical devices, DSLR lens hoods, or even like a low-hanging fruit of can this be something that IKEA can use as like a flat pack ship, send it to the customer and deploy it. So again, physical models, digital renderings, and just sort of like a more sort of fine prototype also to try to see how can this rotation of geometry be itself used as a dimmer, right? The more you rotate, the more the fins open up, the more the light comes out. So it's performing a dual function. Can this be something that can be used as furniture, flat pack, when you don't need it, keep it somewhere, and whenever you need it, you can deploy it by just rotating it. And this is something that we further developed too. So now sort of trying to scale up, how do you make the same mechanism in a larger scale? What is the thickness of the material? What is the thickness that we need that is not too wobbly, yet be able to be sort of cut very easily. So we ended up using PETG, which is a polymer plastic, to make like a larger scale of the same mechanism. And you can see its deployment. If you just pin two ends of the mechanism, and you can use it as a table. Some sort of detailed shots. So again, the idea of like, there's not sort of the method of making, and the geometry itself is the design, right? Like these are not sort of separated where you have a design and you use some method or some geometry to facilitate that, but there's a sort of distinct connection between the design and the working of this mechanism.
Imagine entire buildings like this, you'll be able to redefine the whole skyline. The office building simply collapsed after.
Means it also sort of reminds me of a lot of the work of Buckminster Fuller, where like a lot of his earlier work, he talked about like this the geodesic dome, the deployment. You must have seen photos of the helicopter coming and deploying it. So it almost goes down to like, I look at that as a rigid mechanism, has a lot of parts, and how can this be a more sort of compliant version of the same, you know? So to sort of see, and again to Sanjay Sir's point about how, like shelters, right? Like that's also one more area that I want to explore is what is right now the largest one which I've made is a table in the living room. How large can we go? Can this be something that can be deployed in areas of calamities? Two people would sort of uh, bar down two ends and two people would deploy it. Can that become a shelter itself? If that does not want to be a shelter, it can be a scaffolding. Can that be a scaffolding and some other stronger material, ceramic or concrete, that can be laid on top of it? These are just interesting ideas that are worth exploring. As I mentioned,
You can start a company called House in a Box.
maybe, yeah.
Carry home a box and you deploy it and sell it from the house.
So as I mentioned, with different scales have different forms of fabrication. When you start becoming really small, the fabrication method also changes. So in the end, we also have like, as I've earlier mentioned, it's not just from the designer's point of view, but I collaborated on this with the Harvard School of Engineering, and we worked together to even quantify, can we digitally simulate this thickness of material to be able to show us as in the simulation how much it's going to expand or contract when deployed. And hence Kiriform is a mechanism that can be created out of flat sheets and easily deployed. And sort of one of the sort of current application that we are also looking at is how small can we make this. So I'm collaborating with one of the PhD student, Duigo, from Germany, to try to see if this can be made small enough to be able to be used as a stent for brain aneurysms, made with nitinol, which is a shape memory material which remembers its shape. So based on certain temperatures, can this be deployed directly inside the body? And my last sort of project that I wanted to show you is a project that would sort of follow trying to find a finite solution to a problem. So when COVID hit, majority of the universities in the US also shut their doors down. And I think it was really bad overall for the world, but that was also one point in time where designers also got a chance to see how they can directly help people in terms of using their skills that they have to design things for people, for patients. So one of the projects that I got involved in was trying to design a barrier, a hood that separates a patient from a doctor. Because at that time, there were so many COVID cases happening that every person who used to come to the hospital had to be considered as a COVID positive patient. That's why there was a big team of people who set out to design a barrier. And that's where sort of the Apollo 3 patient isolation hood comes. So there was a massive Slack group of around 200 people, ranging from people from, this was based in Boston, right? So people from Charles MGH Hospital to Boston Children's Hospital, a lot of people and scientists from MIT, Harvard, all of them trying to help in any way they can. The doctors had a certain criteria of how this barrier should be. It should be optically clear. It should be very easily disposable. It should be lightweight. So these certain factors. So a lot of the different ideas were discussed. My role in this project at the start was just helping others visualize their idea. As a designer, that's what it's very common for us to do, right? People have an idea, how can we make a 3D model and try to showcase how it's working. So I spent quite a bit of time on that. But one of the issues was majority of these designs which were being portrayed would take a lot of time to fabricate because they were very complicated, had a lot of parts. So I tried to look at, through my masters and through my sort of experience with working with flat sheet materials and origami, is there a way that we can make a 3D form out of flat sheets? So that's why I started to dive deeper into origami to see, can we use the stock material of a flat sheet and be able to make it into a hood, and try to see if we can achieve all of those pointers given by the doctors. So again, locked in my house with a small vinyl cutter, I was able to sort of use regular paper and just make a lot of iterations. While the group was pursuing the other projects, I decided to sort of like showcase like, hey, you wanted something designed quick, origami is the way to go. And hence I put forward my idea, and that's where they decided to go forward with this sort of design. So as you can see, the Apollo isolation hood, it relies on being cut out of a flat sheet. You can see these two green pointers. Those are something that we call as pivots. That's the pivot against which the sheet can be folded over. So as you can see that as an example at a smaller scale. So as you can see how in my house, I was just simulating how this could be actually used by a human, ideas of scale. And then we got access to the shop where we started making full-scale prototypes of the same for the doctors to test out. So we went through a lot of different iterations, like constantly talking to doctors, trying to see if things are working fine, if their doctors are finding it comfortable or not. And just based on different iterations, this was like the final design of what we made, where it was made out of 116 thick PETG sheet. As you can see the pivots here, this whole section overlaps with this section, hence it gives it like a double thickness where stability is needed, while the rest of the portion is super light. And you can see it being cut under like 20 minutes through a cutter. And even we had to also look into how do we communicate, how easy it is to fold and form to someone who doesn't have a background in design. So what I was mentioning about like the double thickness, where this area comes and aligns with that, the base one folds to and forms like a compliant hinge. And this is like sort of the photos of like the final product. And we ended up fabricating around 20 of them, and they were actually used in the hospital at Mass General. And sort of it was interesting to sort of look at this whole process where, like, because during that time all the plastic was being used for face shields, right? So we had to be very conservative during when we were using material. So we decided to follow that any major changes that we do, we would do it at like a level of using paper, but the minor changes could be done within the old larger models. So we are not wasting material constantly. So that's something as a feedback loop, which is very important. When we used to fabricate it, we used to just make cutouts in the changes in the larger models, give it back to the doctor so that they can test out if things work. So that just trying to highlight the importance of sketch modeling. You know, everything does not need to be completely fine. Like, you just can use regular materials to just give you the sense of what it should be, and then make the final model when you have the resources and time. So again, it was like a collaborative effort amongst a lot of people from different backgrounds via Slack as a medium. We also put the design open source on GitHub so that we are not trying to keep the knowledge with ourselves, but anyone in the world can just download the files and make their own based on their available resources. You don't need a fancy $150,000 cutter to cut it. As long as you have the sort of the map, you can even cut it by hand if you want, So it also tries to democratize the knowledge with anyone without infrastructure as a barrier. And so as in summary, started off with small paper models, going to full scale, to being actually deployed and used in Mass General Hospital. And then eventually it also became a part of an exhibition called Creative Responses to the Pandemic. And it was exhibited in Cooper Hewitt Smithsonian Design Museum for a year, which ended in this March. So that is the end of my presentation. Had to go very quick. Again, if you have questions and comments, I can take them now. And also, if you need to see more projects, you can definitely look at my website and connect with me. Thank you. Yeah, it's scannable, hopefully.